Good day, everyone. I want to thank you very much for joining us on today's webinar. My name is Matt Gawardi. I'm a Senior Product Marketing Manager with Infoblox. And for today's presentation, I'm very excited to announce that we have John Belamaric, a distinguished architect at Infoblox, who is going to walk through containers, orchestration, and microservices and give you some best practices and things that we've learned from our expertise and experience over the past several years. I do want to cover a few house cleaning items today before we do begin the presentation. This webinar is being recorded, so in case you miss a portion of it or want to share it with a colleague after the webinar, you'll receive a link afterwards that you can share and view on demand. In addition, you're going to be in listen-only mode throughout today's presentation. If you have any questions, please use the Q&A chat feature or tab at the bottom of the On24 platform. So just click on Q&A, type in your question throughout the presentation, and time permitting, we'll answer as many questions as possible. If we do miss your question, we'll try to answer them afterwards as well. Again, I want to thank everyone very much for joining us for today's webinar. I'm going to turn it over to John Belamaric, Distinguished Architect for Infoblox.
Thanks, Matt. Hello, everybody. Welcome, and let's get started. So today we're going to cover a few different things. Start with some background around what Infoblox is doing within the microservices and container environment, and then I'll talk a little bit about the general high-level primer on containers and microservices and why they're a big thing now before I dive into specific Infoblox experiences around this. So, as I mentioned, we've been doing this, or as Matt mentioned, we've been doing this for some time now. We've built our own SaaS offering based on a microservices architecture. And so as part of that, we've spent a lot of time getting involved in various industry organizations. In particular, the CNCF is one that we've spent a lot of time, which is the Cloud Native Computing Foundation. We've spent a lot of time in that organization. In fact, I'm very happy to say that one of the open source projects that we participate in, Core DNS, was accepted recently as an Inception project there, and I'll talk more about that later. We also work closely with Docker. We're a technology partner there. We're building some IPAM integrations for Docker, and I will, again, talk about that a little bit more. But one of our own engineers, Yang Teng, was actually recently honored earlier this month at DockerCon as one of the top contributors to SwarmKit and Docker. This is the cloud native landscape from the CNCF. The little box there in the middle that's highlighted is Core DNS, which I mentioned earlier, and we'll talk a bit more about later. One thing I'm going to do here, a couple of times I'll pause and take a poll and try and get a better idea of where the audience is as far as level of knowledge, and help me tailor the rest of the presentation. So first, if you can just fill in the answer here regarding where you are in your container deployment within your organization. Are you just working in a lab? Do you have most of your things containerized, most of your applications out there already in production? Please take a moment, and then I'll go forward. Okay, so looks like most folks aren't sure where their organization is. That's not surprising because we have mostly networking folks on the call, and so the application teams are usually the ones who are driving forward with the container deployment. And so this is, I hope, then given how early people are in this development, I think some of the primer material should really be helpful. So we can dive right into that. Well, as I said, we are building our own container orchestration platform for our internal use, not to distribute. But as part of that, of course, we've had to give a lot of thought to why we might want to do that, why we would want to move to container microservice architecture, and what problems that solves for us. So essentially, any application has some very basic goals, and this is kind of motherhood and apple pie. Everybody knows this and believes this, right? You want your applications to be available, you want them to scale well, you want them to be secure and supportable. there's a few things you get out of microservices that are harder in other applications. That's agility around adding functional enhancements and being able to roll out new features, those functional enhancements, with low risk. So those are the goals. Any architecture that's going to meet those goals, really needs to meet these criteria, right? It needs to enable you to break the application into small parts, independent parts. What that does is allows the availability to be managed on that individual component. It also allows the functional development to be focused on an individual component with a single team. In order to get the availability and the horizontal scalability, you need to load balance across multiple instances, and you need to really put work into enabling separate versions that run concurrently so that when you do rollouts, you don't have to have any downtime. The industry, of course, knows all this and has come up with the solution du jour of containers and microservices. So why containers and microservices? Why is that the solution? Regarding containers, one of the things that's really helpful for them is that they provide a self-contained, immutable unit of management. What does that mean? Self-contained means that you build in all the dependencies. So you're generally going to run a single process within a container, and you're going to build in all the dependencies that process needs. So all the system libraries, anything it touches, it gets. And that way you can deploy that completely independently of anything else. The only dependency is the kernel in Linux, typically Linux, but you can run it on other platforms as well. But making only the kernel the only dependency means that if you deploy two containers side by side on the same host, they share the same kernel, but they don't share any of the system library or the stack, so that when you want to upgrade one, you're not affecting any other container that's running on that system. But speaking of upgrade, we also want these containers to be immutable, meaning that you don't log into a container and make changes and upgrades and modify the software. Instead, you build a whole new image, you tear down the container, and you build up a new image. So by working on that basis of the immutable container, independent container, we can build on top of that this concept of a microservice. So generally, traditionally, applications are large pieces of software that have many components that interact, and there's a lot of dependencies between those different components. The idea of the microservice architecture is to take that application, break it into pieces. Essentially, it's almost turning it inside out. That's how I like to think of it. You break it into these pieces, and each of those pieces controls its own set of data. Any coupling between those pieces is done over a versioned lightweight API. And those individual pieces need to scale independently. So what does that mean? It means that you may run multiple copies of a given component in the application, but you don't need to run multiple copies of the entire application. In order to be effective, these services should be designed around the functional aspects of the application, not the technology function. So when designing an application, often people tend to think about the technology components of the application. So there's a web server, an application server, a database server. These are different components. They talk to each other. And traditionally, we would scale maybe the application tier. We'd scale maybe the web tier. Those tiers would scale independently. Here, what we do is instead break the application into its functional areas. So a functional area might be something very simple like a pricing service or a shopping cart service, right? So those provide one small component of the application. That individual component will have that full stack. It may have a web server. It may have some sort of application server. It may even have its own database or at least its own schema somewhere. when you do that, then you can have a completely separate team working on each of those individual pieces and advancing the functionality of each of those individual pieces without the dependencies on the other parts of the application, as long as they use a versioned API to interact. That's the critical piece of why each microservice has to control its own data. So this architecture really does work to meet a number of those goals that we saw in the beginning, because each individual microservice can run multiple copies of itself in order to scale for the incoming traffic. You also get high availability, because if you're spreading these individual instances across hosts or availability zones, then a failure in one of them doesn't cause the whole service to fail. One of the challenges, though, of course, in microservice architectures is that you end up with a lot more services talking to each other, and much later in the presentation we'll delve into a little bit of what that looks like. So for any given microservice, it goes through a life cycle. So the life cycle basically defines how that microservice is created, how it scales, operates, and how it eventually is destroyed. So you start with a declarative definition of what the microservice is. So this microservice is a pricing service. It consists of a container that runs, this particular image, and another container that runs this image, and they're hooked up in this particular way. And there's a sort of unit of scale. So in some of the orchestration environments we'll talk about later, you have a concept of pod, and a pod is a sort of group of containers. It's the unit of scale. You can run replicas of that pod, for example. So that's how this life cycle works. The definition gets stored in a service registry of some sort. The orchestration system picks up that definition, and when somebody says to deploy it, and it will launch the individual containers that specification defines. Then those will be running in production. Those will be emitting telemetry, and those have to go somewhere. We'll talk a little bit more about that later. But they'll be emitting telemetry, and there needs to be something sitting on top of the telemetry and the orchestration system that decides when to scale, that is, when to add additional replicas of any given microservice. That's part of that operational procedure that's going on. Eventually, maybe you're taking down the application, or you're upgrading and going to a different version of the microservice. You're going to redirect traffic to that new version. You're going to tear down the old version, and that's the destruction of it. So that complicated life cycle isn't something you're going to manage manually, and especially when it's something that needs to happen continuously. Traditionally we deploy an application, we have a window of 6 hours or something where we go and we build the new version of the application, and the website comes up with maintenance mode, and we're working at it. But we're trying to avoid that. Part of the goal of these cloud native architectures is to avoid any downtime. So you can't be manually managing that lifecycle process. That's where the container orchestration systems have come into play. So these grew out of the need of these microservice architectures, and the fact that the specific Docker engine, which traditionally was used to manage containers, really was originally made for a single host environment. So you have this Docker daemon that runs on a Linux machine, and you talk to that with an API, and you tell it to start up containers and tear down containers, and it can connect them together on a bridge in the Linux host. But with just that system, of course, you can't achieve the availability and the scale because you're confined to a single host. So the industry, or a number of people, Docker included, came up with different systems to orchestrate and coordinate those Docker engines that are running across multiple hosts, so that a single application can be controlled from that can be deployed and that lifecycle controlled and managed from that single system across all those different hosts. These manage the storage of the definition, as we talked about. They create and destroy individual instances of the microservice. They also, of course, have to connect all these things together. So they also, there's a lot of work done around managing the networking between the containers that are spread across a number of hosts and load balancing across those containers transparently so that we get the availability we want. The CNCF, like I said, Cloud Native Computing Foundation, whose charter is really to promote these kind of cloud native architectures, took this concept that's evolved and put a little bit of a structure around it, and essentially they've defined this stack for the concept of orchestration. The end users of the orchestration system can view it this way. The lower level is the infrastructure layer. That's the physical network. So usually we call that IaaS, infrastructure as a service. That could be AWS, it could be bare metal, it could be OpenStack, it could be anything that manages the underlying virtual machines and their connectedness with one another. Then on top of that, which really is where you enter the realm of these cloud native and microservice architectures and the orchestration systems. So you need the ability to provision the different containers on there. You need the ability to run those containers. That's the runtime. And as we said, orchestrate and manage and define applications. There are 3 big orchestration solutions out there. There are many more. This is still very much an early and very rapidly evolving space. But the 3 big ones out there today are Kubernetes, one called DCOS, which is what the open source evolution of Mesosphere, their Mesos and Marathon products have become, and then Docker Swarm. So, excuse me, Docker has solved this problem of Docker being a single host solution by building an orchestration platform that's built into the Docker engine itself. So individual Docker engines can now communicate with one another, and they call this Docker Swarm. There are a few differences between each of these. They generally serve the same purpose, but Kubernetes is got a lot of momentum right now. It was originally started by Google based on their internal Borg, but an open source version of it, and they donated it then to the CNCF, which is really kind of how the CNCF got started. And it can use different container runtimes. So one of the things that probably if you're new to containers you don't realize is everybody thinks Docker, but Docker is really just one way of building and deploying containers. It's the most popular way. It's the most widely used way, but in reality there's several other ones. And given Docker's position in the industry, there are other industry players who don't want Docker to take over everything. And so they're working hard to compete with Docker. One of those is one of the things that came out of that is what's called RKT, or Rocket, and that's an alternative runtime for containers. And you can take a Docker image, or what's now called an OCI, an Open Container Initiative image, and it can run it just the same as Docker would, but it's all vendor neutral. In fact, Rocket and Docker's equivalent piece called Containerd have also been donated to CNCF at this point. The Mesosphere and Marathon had a lot of early momentum, and when we were building out our cloud and our PaaS layer, as it's called, we adopted Mesos and Marathon, and so those are the core pieces used in our NGP. Because at that time, Docker Swarm didn't really exist, and Kubernetes was quite immature. We are considering some other options now. But so Another poll here, if you're aware of your organization using a container orchestration platform, please indicate which one. There are quite a few here, but there, like I said, are probably another 10 at least out there that aren't available. Aren't listed on the poll. Okay, so all right, well, that's good to know. So Kubernetes, we'll talk more about Kubernetes in a little while, and as I said, that is something that's really leading the way right now. Docker Swarm is also pretty popular, but is immature, and that's probably why we see low adoption here. I'll talk a little more about Kubernetes later. All right, so I mentioned that all of these orchestration systems need some way to hook all these containers together and do the networking between them and do the load balancing. So we'll talk some more about that. There are essentially two leading solutions in this area, and when I say leading solutions, this is really the framework that's the orchestrator provides. It's not actually the networking service itself. So the Docker has something they call the container networking model, and this works with a standalone Docker engine, or it works with a Docker Swarm. With a standalone engine, you're more limited, of course, in what you can do because you're on a single host. But in the Docker Swarm, it allows you to create virtual networks between the different hosts. Container network interface actually does basically the same thing. They're very similar in they're functionally equivalent, I would say. They're different specifications. Docker's only, of course, works with Docker, whereas container networking interface works with Docker or with Rocket or with some of the more obscure container runtimes that are out there. As I was saying earlier, Docker has a lot of weight and a lot of prominence in the industry, and so all the other companies within the ecosystem don't really want to necessarily contribute to Docker's level of influence, and so that's part of where container networking interface comes from, and all of these other solutions like Kubernetes and DCOS are all supporting CNI, and that's what they build in and use within their deployments. So each of these, both CNM and CNI, are driver-based. So essentially, you'll go in and you'll say to Docker, create a network using the bridge driver and name it foo. What that does is it will create a Linux bridge, so a bridge within the host, and when you launch a container, you'll say, okay, launch this container and attach it to network foo. So that container will get attached to that bridge. If you create several bridges within the same host, you're creating isolated networks. There's no connectivity between them, and so you can attach containers to those different isolated networks. So the bridge is the default driver in Docker. That's what you see in the single host environment. Not really that useful. In the Swarm environment, there's something called the overlay driver, which uses VXLAN to connect bridges on each individual host together into a single layer 2 address space. So that's, from the point of the view of the container, it's attached to a single segment with all the other containers that are part of that VXLAN. This is obviously much more useful. It allows a lot more flexibility. It allows the scale across different hosts. It has its own issues because VXLAN is an encapsulation, but that's pretty effective. It does require the swarm mode because the individual hosts have to communicate with one another in order to coordinate this, and the swarm mode is what allows that to happen. There's another driver, there's actually a whole bunch of them, but another one that Docker ships is a Mac VLAN, and this one is interesting, and it's good for it's a good example for where the Infoblox IPAM would come into play. But essentially, this enables you, when you create a virtual network on a given host, you associate it with a VLAN tag that's on the physical network. And then the containers that get attached to that are essentially directly attached to that VLAN. So the MAC and IP that the container receives will be on that VLAN, which could be, it's an ordinary VLAN in your environment, could have other physical services, physical hosts and things attached to it. So given that type of example, there's not only a network driver available, but there's what's called an IPAM driver available. So the IPAM driver, IP address management, that's very much in, obviously, Infoblox domain, that all IP allocations and subnet allocations that Docker needs to do in this case would come through that driver. So when you're in that, if you want to use that VLAN driver, you'd run into a problem where you're allocating IP addresses on some VLAN which may be routable throughout your organization, and of course, if Docker is completely controlling the IPAM, you're gonna have a big problem because Docker allocates IP addresses locally scoped to the host, essentially. Like if two hosts bring up the same container, they would get the same IP address if they use Docker default IPAM. So instead, in this case, you'd associate your IPAM with Infoblox. It would be then getting the IP addresses from the address space that's routable throughout the organization. So last poll here, if people can just say whether they know what container network solution you're using. You may be using more than one, in which case, just pick the most prominent one. The ones at the bottom really are just different kinds of drivers. They're different vendor drivers that support each of these different environments. Okay, that's not surprising given it seems people are early in their adoption. If you're using Docker, you're likely to be using the Docker networking, maybe with one of the drivers or maybe not. So it's interesting. So that's really the overview of microservices and containers from a sort of high level. Now I'll dig into a little bit what Infoblox has done in our environment and explain a little bit of the different options we chose. One thing I wanted to mention, I did only talk about the CNM drivers, but the CNI drivers are essentially the same. The stock drivers that ship with Docker, or you can pull down from the container networking interface GitHub site, they really support the same type of functionality. That's why I really only talked about the one. Over the last few years, Infoblox has built out a SaaS offering. In order to build that SaaS offering, we need to build a lot of infrastructure in the cloud for scaling, for deploying applications, and as we add additional applications to that SaaS offering, they'll run on the same platform. In order to achieve that, we have architected it as you're seeing on this diagram. So at the top, that's the actual product offering. So we have one right now called Active Trust Cloud, but there are other ones coming along. Then we have what's called the PaaS layer, and that's we'll dig into in detail. And then the IaaS layer. So the IaaS layer we mentioned earlier, this looks very much like that same chart you see from the CNCF that I showed earlier, but this is the one that we built. Today we're using AWS for our IaaS layer, so all of our SaaS offerings are running in AWS today. On the left, you'll see the service delivery platform. So this is really the back-end kind of office back-end things that are needed to manage all of this and to connect it up with customers and to do billing and this sort of thing. Drilling into the PaaS layer, this is the container orchestration layer. So it's divided into two basic parts. The control plane. The control plane manages all the networking. It's really that container orchestration piece I was talking about earlier. It does all of the service registration, microservice lifecycle, auto scaling. All of these pieces are done there in the control plane. And then there's a set of application infrastructure. The application infrastructure provides an IaaS-neutral set of APIs to provision services that the application may use. So what does that mean? It means you may have several different applications running in your cluster. All of them need to create their own database, for example. Well, you could go directly to Amazon and create a database using the Amazon APIs and the Amazon tools. But then if you wanted to move to Google Cloud or you wanted to move to an on-prem installation, then you're stuck with having to essentially re-implement parts of your application or whatever it is that's deploying. Really, for us, it's the SDP that deploys these things. So instead of tying directly into those services, even if we're going to use an Amazon native service like DynamoDB on here, we put a layer on top of it that's an IaaS neutral layer API. So all of our software is built to talk to those APIs and allow us to move applications and deploy them in different clouds without major rework. Today, we're, like I said, running Mesos and Marathon, and that's what you'll see on that control plane. We are considering moving to Kubernetes and taking a look at that, because these days Kubernetes seems to have a lot more momentum in the sense of there are thousands of developers working on it, and it's adding features very rapidly, some of which look pretty attractive to us. So that's how we implemented the control plane: Mesos, Marathon, APIs, application infrastructure with their own IaaS neutral APIs on top of them. For networking, it was pretty interesting. We had, this was probably two and a half years ago, and container networking at that time, although it doesn't sound that long ago, at that time was very immature. And so there were only a few options out there. One of the options we looked at was Weave. Weave is still there, but at the time, Weave had its own proprietary encapsulation protocol, which didn't perform well. And of course, if anything went wrong with it, you're debugging their code. So we were hesitant to go with something like that. There were a few other options, like Calico and VXLAN, just directly from the Linux kernel. But we realized, in researching this, we looked at a paper by Google that talked about how they do it internally, or how they've done it traditionally anyway. And one of the things they note is that, there's no real need to do this at layer 2, which is what all of the solutions were really advocating at the time, and really to this day, for the most part, still do. But something like VXLAN, right, it creates a layer 2 tunneled through layer 3. And instead, it's much simpler if you build a static routed environment. So what we ended up doing is something similar. If you are curious, you can look up something called Ubuntu Fan. But ours is not, we don't use that technology directly, but it's similar to what we do. It's just a very simple, we decided, all right, one of our clusters will have at most 256 hosts. So we're boxing ourselves in, we're losing flexibility, but we essentially then, we took a /16, and then for each cluster we assign a /24 for the container networks, and we just fix it at that. So, it boxes you in, it limits you. You can only have, 250 or so given containers running on a host, and you can only have 250 or so hosts within a cluster, but it dramatically simplified things. And given our flexibility in running this today completely in the cloud, we can easily tear up and bring up and tear down new clusters. So if we decided to, say, change the topology significantly by, using a /18 or something instead of, we could we could actually just deploy a new cluster pretty easily and move traffic there. So rather than worrying about the complexity of the different layer 2 solutions, we went with something very straightforward and very simple. Given that, though, that since then things have evolved quite substantially. If you look at some of the tools like Kubernetes, for example, it assumes that you have a pretty flat address space. So we may have to revisit that, but for today it's working very well for us and pretty simple. Essentially what we do is we have, of course, each host has its routing table, and we have defined somewhere in our service registry what the topology is, and then we have an agent sitting on each host that basically is ensuring in a declarative manner, looking at the data of what should be, and is ensuring that the routing tables on each individual host are set appropriately, and that allows us to reach everything. For load balancing, again, at the time we initially built NGP, the container orchestration systems themselves weren't really very mature. Today, Docker Swarm, Kubernetes, they offer a variety of ways of doing in-cluster load balancing, but at that time, such things weren't available. So we did build our own there as well. And the interesting thing is, because we're running DNS, which is primarily UDP, and we want to take advantage of Anycast, we had to come up with ways of not just doing the in-cluster load balancing, which we do through IPVS. It's a Linux kernel module built into the kernel, but also we had to worry about how we can take the internet scale traffic and break it into small enough bits that individual IPVS hosts that are Linux hosts that are managing our IPVS load balancers could handle. And so for that, we ended up using ECMP through GRE tunnels. For us, all of that works in the cloud. That's great, but we also have products that we'd like to deliver on-prem, products that are managed via the cloud but delivered on-prem. So part of that, we've built an on-prem extension to the cloud. So this essentially allows you to have a remote system set up that talks back to the cloud, and the cloud can be used to provision different services on that remote system. So the first application of this is what we call our DNS forwarding proxy for Active Trust Cloud. So Active Trust Cloud is this service we run in the cloud that's like our DNS firewall service, essentially. It allows you to, it will block requests for command and control servers for different botnets, things like that. So we essentially become your recursive DNS service, but we block all of these things. So we want to be able to deliver an on-prem VM or device that customers can install in each branch office, say, and then that can be managed in a single place. All of those can be managed. All the policies associated with those can be managed through the cloud. So that's why we built this on-prem extension, and the first that connection back to the Active Trust Cloud is the DNS forwarding proxy. Should be, which I think is in beta perhaps now. But if you think about that, though, what did we just talk about? We talked about we've got something we can manage in the cloud. We've got something that's sitting on-prem, and we can run containers and run different services on that thing on-prem. So we saw that as a really interesting opportunity. In particular, our first an opportunity to run network services in remote sites, but manage them centrally. So as a sort of experiment, something we've been working on internally is to build what we call a white box router. So today, in our cloud, in any given region, in any given data center that we want to build out, any given region we want to build out a cluster, we need to be able to advertise the Anycast IP address for our Active Trust Cloud service. AWS itself can't do that. It doesn't have that functionality. So we actually need to install physical routers in these data centers and attach them back to AWS via what's called Amazon Direct Connect. Those routers will talk BGP and advertise the Anycast route. And those are expensive, and then and managing them is expensive. And so one of the things we are experimenting with now is taking a generic white box Linux machine with a couple of 10 gig NICs and dropping it in that data center, putting our NGP on-prem management software on it, and then running all of the services necessary directly there on that white box and manage them via our cloud. So it's a pretty interesting experiment, and we'll see where it goes, but something we're working on. All right. I'm going to dive into some things more around microservices and some of the individual specific functionality that you need within a microservice orchestration environment. So one of the things that we're particularly interested in is something called service registry and discovery, or we call it micro DDI, but really it's service registry and discovery. If you think back to that life cycle and to the idea that microservices individually are independently and individually spun up, but that any given application consists of many of these microservices. You see there's a fundamental problem in how these individual microservices, as they spin up, locate the other microservices they need to talk to. The IP addresses here could change very quickly and easily, and so you can't embed IP addresses into the configurations. You need something that's going to keep track of what's running and what IP address it's at, so that something that asks for it can get it. Of course, this is done with DNS today in most of these orchestration environments, and that of course attracted our attention. To give an example of what we're talking about here, these are called Death Star charts. So around the circle are different microservices. So each of those is an endpoint, which may actually be just a load balancer VIP for 100 containers, each of those points. And then the lines between are which microservice talks to which other microservice. So you can see that the level of complexity in these microservice architectures goes up very quickly. This is sort of what I was referring to early on when I said microservice architectures are great for scaling, they're great for availability, but supportability can be a real challenge. Imagine that you have a request that's taking a long time. How do you figure out what's going on with that request? How do you trace that request through all of these individual microservices? Some of these are real challenges. The one that we're interested in is really around the service registry and discovery and aspects like compliance. So just as a context or a side note, Halo is a sort of Uber for in the UK, and so of course we know Netflix and Twitter. They have a lot of microservices today. Even with our one or two applications we're running in the cloud, we already have about 25 microservices. So it really does multiply quickly, and you end up with these kind of situations. When I see something like that, that level of increased complexity, I think about the application developers. The whole point, or one of the main points of these architectures, is to free up the application developer from having to worry about a lot of the details. And so in order to do that, when you have these microservices like this, you end up with a lot of these things around who can talk to whom, and if you're running in a development environment versus a production environment, if you're running in different PCI zones or what have you. I don't want my application developers to have to think about that. And so one thing we're working closely on is something we call policy-based service registration and discovery. I'm actually just about out of time. I'll try and go through this quickly. This is getting into some pretty this is getting pretty far down the road in this development, so it may not be of interest to everybody given people's early stage, but I'll try and get through it quickly so we can get to the question and answer. But essentially, as I said, we're looking at how can different microservices find one another, especially if you're in a multi-tenant kind of environment where you have different groups within the organization deploying things and there are different levels of visibility allowed. And so the service registry and the service discovery function is what allows the things to connect. And we see a way to insert policy-based management in there, much the same as we do with something like Active Trust Cloud. So Active Trust Cloud, we're controlling the access and the visibility to command and control servers for botnets. But really, there's no reason why we can't build a policy system such that we control access and visibility to from one microservice to another within one of these orchestration environments. So to do that, we're building our own policy engine, which externalizes those policies, and you can populate either through handwritten policies or through policies that are pulled from some sort of database or service registry and populate that. This is very research-oriented stuff. This isn't something we're offering as a product at this point. Some of the applications here are, like I said, you can control who can see what, but you also can do things on the registration side. So if you recall, we talked about in the microservice lifecycle, you need to register the microservice needs to launch, the microservice needs to get an IP address. Given that we're potentially in the IPAM process for the container, if we also have this policy engine which can establish policies about the container, such as if the container doesn't have one of these specific labels or tags that indicates that it's been, say, security scanned, then don't allow it to be launched. We can deny the IP address for that. On the discovery side, we can, as I said, do redirect or block lookups from dev to production, things like that. To achieve that, this is one of the reasons we're investing in Core DNS. So Core DNS is a DNS server based, well, originally from the same author of another popular cloud-native DNS server, but it's a sort of improved version of that. Our investment has really been around integrating that with Kubernetes. So we built the Kubernetes integration to allow Core DNS to serve as the service discovery component within Kubernetes, and we're working with the Kubernetes community to make that, in our hopes and dreams, into the default DNS server for service discovery for Kubernetes. So as part of that, we want to add functionality that the existing service discovery can't do, such as integration with the policy engine. Okay, that's all I have for now, and I think I'll hand it back to Matt to moderate the question and answer session.
Sounds great, John. Thanks very much for going through that presentation. And as you can probably tell, John's very knowledgeable and passionate about things that we're doing on containers and microservices. We do have some time for Q&A. A few questions have come in already, but if you have any questions for John, kind of what we talked about or anything else you're thinking about, please use the Q&A feature at the bottom of your On24 platform and type in your question, and time permitting, we'll answer as many as possible. I did see a few come in. I might combine those to simplify the process. You know, one of the things that John went through was just kind of explaining what Infoblox has done with microservices and containers for our own product capabilities. So not meant to be a product pitch, but really leverage his expertise and how we built our solutions and things that we sell to our customers on some of these key aspects. You know, doing a slight commercial with Infoblox, what we're known for is the solutions for, you know, enterprise and carrier grade DNS DHCP, IP address management, and we're also leveraging integrations into things like Docker and containers, as well as virtualization to help automate things like assigning IP addresses and provisioning DNS records. So again, as a customer or prospect of Infoblox, you can leverage some of your existing technologies or maybe future technologies to help automate some of these processes. But again, today's webinar is focused much more on kind of the ins and outs and learnings that we've seen from dealing with containers. A couple of questions came in, John. I'm going to group these together. I was asking kind of, any best practices or pitfalls that you recommend people who are kind of trialing this or thinking about it from a networking perspective, pitfalls to avoid from things that you've learned.
Well, I mean, definitely, as I said, in our early days, we did find that creating a simpler Layer 3 based container networking made our lives easier, made it much easier to debug in particular. But that said, it's a little bit hard for me to say that to advise that that's what you should do today, because the solutions that are available on the market since we did that have advanced quite a bit. And I've used VXLAN and via OVS. I've used Flannel in a lab Kubernetes environment. And some of these, they're pretty simple and easy to get running. But I do expect that in a production environment, you may have some performance issues and other issues with overlays. One customer in a related cloud use case, a couple of customers I've talked to have talked about specifically overlays giving them that kind of problem. And so they tend to build a traditional Layer 3 routed network and assign individual VLANs to individual racks, essentially. Now, that's done more at the IaaS layer as opposed to the container networking layer. But I guess the advice is really consider what level of flexibility you actually need in your networking environment, because while things like Weave and even basic VXLAN and overlays from Docker, they're very convenient in a lot of ways. Often you don't need that level of flexibility like we didn't. We were able to essentially get everything we need by utilizing the flexibility at the IaaS layer and avoiding having to build in those kind of networks.
Okay, great. Thanks a lot. Another question came in, I think it was earlier on, you're talking about scaling. How do microservices know when to scale? Is it something that's automated? Is it something you deal with individually? Or can you give an overview on scaling from a microservice perspective?
That's a great question, yeah. In general, the province of the scaling should be, in my opinion, in the control plane, in the sense that you have a service within the control plane that's going to monitor telemetry. So typically, some of these applications, these microservices, they'll emit metrics. One common solution for digesting those metrics is something called Prometheus. That's another CNCF project, but there's, of course, many others. You take those metrics, and you have to, of course, establish policies then. And this is something that, right now, there's no hard and fast way to make that decision. So, for example, Kubernetes, as far as I know, doesn't have a decision platform for making that kind of decision of when to autoscale. Rather, it's something you can do. It has the declarative machinery to say, there's 3 replicas now, I want there to be 20, and it'll take care of spinning it up to 20. But when that decision is made isn't part of that infrastructure today, as far as I know. So that's, in our environment, what we're looking to do is take that same policy engine we've built for really, it will eventually be in our Active Trust Cloud in the back and behind the scenes. That policy engine will also allow you to define those scaling policies to say, I need my if my QPS gets above this level, I need to scale up. And so then in our case, the Active Trust Cloud is emitting these metrics of what the current QPS, or maybe it's just CPU. It's simpler, right? Okay, CPU utilization on this particular host is getting high. Therefore, we need to add more replicas across different hosts, that kind of thing. So that policy decision for us, will come out of that policy engine, which can be loaded with policies by our operators, so they can define what those criteria are, what those policies are around scaling. But it's not actually something in the general orchestration environments today.
There's a follow-up question that came through. I'm not familiar with it, but hopefully you are. It was kind of a question/comment. Can you scale this through either ECS or CloudWatch Lambda? Is that something that can be done, or?
Sure. I mean, ECS, we're not using ECS internally, and I haven't looked really closely at it, but yes, I believe it offers that kind of feature. So AWS offers, there's a sort of tension here even where it's sort of like how much of AWS native services do we use, which binds us to AWS, versus how much do we build ourselves, or do we, like I said earlier, build an API, then an IaaS neutral API between us and AWS. But essentially, for the IaaS layer scaling, AWS has these resource groups, and you can set these scaling policies there. On ECS, I expect they have the same thing, but I haven't looked closely at that. We do use Lambda for our canaries, for our synthetic transactions throughout our thing, but we don't use them for auto scaling today.
Okay, great. This question might be between you and I, John. I'll kind of give you the first answer and let you follow up. But it was, talking about any processes built in for the product for security between microprocessors and containers, prevent malware and other attacks, something that's action-based rather than signature-based. And I'll jump in first and let John add any color he wants afterwards. Really what John was focusing on was kind of containers and best practices and how we've used containers and microservices for some of our own products. We use something like Active Trust. So from a product perspective, what Infoblox has and what we can deliver to our customers, we have products around securing DNS through technologies like Active Trust and advanced DNS protection that really help you reduce a lot of the risk from a DNS-based exploit. So one of the big pain points from security is DNS meant to be wide open, allow everything. As a company, what we focused on was trying to reduce some of those security risks. And as you mentioned, you're trying to do much more than just signature-based. There's really three key ways you want to think about security from a threat detection and mitigation point of view. One is a signature, another is reputational, and a third is behavioral. And we have solutions we built around all of those to kind of help reduce some of those risks. Again, this was not meant to be kind of a product pitch per se, but since the question came in about what we're doing to prevent malware and other attacks, that's what we're doing to help our customers from dealing with those issues from DNS-based exploits. So it's a great way to add on to your existing security solutions to reduce some of those risks. Anything else you want to add, John, in terms of color for security from a container or microprocess perspective?
Well, like as you said, that really most of this webinar I haven't been talking about product. It's actually product we deliver, other than the IPAM driver and the Active Trust Cloud, which are really I was just more in talking about how we build it internally. But there's always our Active Trust Cloud. The only it's all built in AWS. It's all behind the private addressing within AWS, except for the Anycast address that we're pushing out. But so internally, we have a number of different security protocols, but it's not really part of the product we're offering.
Okay. Yeah, and again, I just wanted to reinforce kind of that message kind of merged two things, kind of the topic today as well as the products that we sell. So again, we're helping on a DNS, DHCP, IP address management, automation security. So if you have those kind of questions, we can definitely reach out and get you more detail. I think we have time for one more question that came in, was asking about kind of the audit trails from scaling. So, when it's running, the license costing, audits of application servers, running containers, any suggestions or feedbacks or learnings that you've seen from auditing, from scaling and usage?
Well, given that we're running all of this in AWS, they keep very careful track. But, realistically, the cost controls have to be part of, I talked about the idea of building a policy engine that you can inject policies into that control the auto scaling. I mean, that probably should weigh into what those policies are as the cost considerations of the different containers. For auditing, as far as what's been created and what's been destroyed, you'll get some of that out of the orchestration environment, either through if it's got logs that are being pushed to some sort of logging server, or some of them may keep an audit log internally, but I haven't really looked closely at how that's done.
Okay, sounds great. I appreciate your feedback and kind of going through those questions. We're at the hour mark. We try to keep it within an hour because we know your time's valuable. But you will receive follow-up. I did get several questions coming in. That's about a copy of the slides or recorded version. You will receive both copies of the slides as well as a recorded version that you can view on demand or share with somebody else. If you have any questions you thought of, afterwards, we didn't quite answer your specific question, feel free to reach out to us, and we'll try to get John or some other experts to answer your questions regarding containers and what microservices, kind of some of our learnings along the way. And again, I want to thank everyone very much for joining us for today's webinar. And at this time, today's webinar is now concluded.